Good afternoon, Daryl. Today, Victoria and I are going to discuss our building design and material analysis. Material testing and analysis is performed to determine the fundamental properties of the material when subjected to service and environmental loading conditions. Comprehensive material analysis helps engineers and architectural designers evaluate and quantify whether a particular material is suitable for a specific application. The material analysis for engineered structure is fundamental in guaranteeing the design of a structure surpasses its total intended loading requirements. The structure must be reliable, properly tested, and analyzed before construction begins so to prevent a potential failure. The dimensions and details of every construction element depends on the characteristics of the material used for the construction and the external forces acting upon the structure. These elements must be determined correctly during the design process to ensure that the building is safe for occupancy. The steps taken to develop a suitable design consist of professional architectural drawings, construction element explanations, and detailed material analysis. This report will outline the design and theoretical analysis developed for a 12-story office building. The success of a structure depends on efficient and accurate planning and design. To ensure the design of a structure was accurate and safe, several stages and procedures were required. The first stage, the pre-design. The pre-design phase established the goals and design criteria for the project. The building specification required for the structure be 12 stories and incorporate 5-meter unsupported compressive and 9-meter unsupported flexural members in the design. The plan was designed to ensure compliance with the L240 deflection design criteria. A conceptual design and rough sketch of the building was developed at this point. Stage 2, the schematic design. The general design of the building was established and floor plans of the structure were developed. Once the initial architectural drawings were completed, a review process commenced in order to discuss alterations to the original design. This review period allowed us to initiate material analysis and design criteria to ensure specifications and satisfied loading requirements were on target. The third stage, design development. Also, the structural systems were finalized and detailed analysis of the building materials were completed. The finalized designs were compared to the proposed design and necessary changes were made. Once the factory load requirements were satisfied and all checks and balances were completed, the design was finalized. The final architectural drawing was completed to illustrate the proposed 12-story structure. Here is an architectural drawing of our building. It may appear to be longer than wide, but the overall dimensions are 31 by 31 meters. Here's a diagram of our building design which illustrates the tributary widths for column A and column B as well as beam A. These areas have the largest trib area and unsupported lengths used in the material analysis.
Full loading analysis will be done for the 2 columns holding up the first floor and 1 beam. So the 1 column with the greatest tributary area with only vertical loading and an external column with the greatest tributary area that has combined stresses. And the beam, as Jacob referred to earlier, is the beam with the greatest tributary area. So they're column A, column B, and beam A. So the first column analyzed was column B. So that was the one in the center. It only has vertical loading. We chose to do this one first because we were going to use the same column chosen for the external column, column A. And because that one has combined stresses, it was easier to just use whatever column we chose for this as a starting point for column A. We found the load for the roof. The floor is 12 to 2 and the first floor. And the first floor was analyzed separately because it has a live load of 4.8, while the other floors have a live load of 2.4, and those are all found in the building code. So once we found all those loads, we added together and we got our total load. And that can be used to find the required inertia for the column that we're going to choose. So to solve for which column size that we needed, we had to find the required moment of inertia. So using Euler's critical load equation, we rearranged that to find I, using the total load of the floors as our P value. So using all the values in this table and the weight of the floors, which was on the initial side, we found the I value required here, and based on that we went to engineeringtoolbox.com and found hollow steel tubing that was the appropriate size and had an I value just bigger than what we needed. So this alone tells you that it will hold, but we also solved for the critical load of this chosen hollow steel column, and it was much higher than the load of the actual floor, so it was sufficient to be used for column B. Column A has vertical and horizontal loading. So first we did the vertical loading, and same as for the column B, you find the load of all the floors and get a total load, and that is based on the tributary areas. So same as before, using that total load, you can find a required moment of inertia, and for just simple calculations, we used the same column that was chosen for column B, and it did pass the vertical load, but next it has to be analyzed for the horizontal load. So now we're looking at the horizontal load on column A, and as you can see here, there's a wind load applied along the length of the tributary area, and to analyze that, you basically rotate the column 90 degrees and turn that into a UDL on top of the column, and so that can give you your max bending moment. Initially, we used the same column that was used for column B, but once we did all the analysis, it didn't pass the combined stress. It was over 800 MPa, which is way too high because the yield strength of steel is 350. So we chose a new column with a higher I value and area, and this new column was analyzed for combined stress, and it passed 295 MPa, which means that the column is safe enough to hold up the horizontal and vertical load. Next, we analyzed the beam that was holding the most load, or had the greatest tributary area. It was beam A, which has an unsupported length of 900 millimeters or 9 meters. So the tributary area was 54, and once we accounted for all the load, which is only for the floor that it's holding, because it doesn't support every floor above it. So the live load concrete joist is factored, and that gave us the total load. And if you multiply the total load by the length of the beam, then that gives you a UDL on the beam. And to solve for the I-beam that was sufficient enough to hold that load, we used the allowable deflection criteria, which was L over 240, and the max deflection equation. So if you use that and rearrange it, you can solve for the I required. And we solved for the required inertia and chose an I-beam that had an inertia slightly bigger. And with that, we were able to analyze it, and it passed the combined stress, and it also, not combined stress, the bending stress. It had a bending stress lower than the yield point, and a shear stress of 4.03 MPa. Next, we will look at the theoretical load if it was increased by 75%, and we'll analyze that for the beam, both columns and the beam. The first column analyzed with a increased load of 75% was column A. So to increase the load, you multiply the original load on the column by 75% or 1.75. With this value, we can plug it into Euler's equation and solve for a new I required. Because the column is already existing, you can't just replace it with a new size column. So we added steel plates on either side at the same width of the existing column. That way it was symmetrical about the neutral axis, and the parallel axis theorem was needed. So to solve for the new inertia of the column with the added steel plates, you just took the inertia of the outside, so BH cubed over 12 of the outside minus the inertia of inside. That gives the new total inertia, which was analyzed, and it was sufficient to hold the vertical load and the combined stresses. Next, column B was analyzed, and it follows the same principle. Steel plates were added to the sides. Inertia total was calculated, and it was plugged into Euler's, and it was able to withstand the critical load. It was lower than the actual load from the floors that were increased, and the inertia was much higher than needed. The more tricky one was when the load was increased on the I-beam. Now, because the top's already covered, you can't make it symmetrical on both sides, so we added a steel plate on the bottom, and with that, we chose something thicker, so we didn't have to do as much hand calculations, and the parallel axis theorem had to be used, and we solved it, and the inertia was high enough to hold it. And this is something that is done quite often.
So in conclusion, the designing and analysis of this building was effective in demonstrating how real-life design and structure analysis are done. By reanalyzing each column and beam with an increased load, it demonstrated the real-life scenario where the use of a building is changed. With the changed use of a building, the load probably would not be increased by 75%, but it shows that if needed, any column or I-beam can have material added or increased to increase the strength. The analysis of each loading could have been much more extensive, meaning the weight of each column from each floor should have been accounted for, and self-weight for the beams and columns would have been factored in. Also, the joists would have been analyzed as point loads rather than UDLs. For the purpose of this learning, structural analysis, the compressive and flexural analysis, deflection analysis, and full loading analysis done in this report is sufficient in meeting the learning outcome of Civil 14 and Civil 56. Thank you.